Okay, so in the next 10-15 minutes, I'm going to talk about bias in machine learning models and why, as computer vision researchers and engineers, we care about that. And we try to do something about it. All right, so let's just start with an example to see when people are talking about bias in machine learning algorithms, what they're talking about. So in this example, say I've gone out, taken a picture, and I don't know the name of this animal. And I just remember there's a TensorFlow model that either I can use the web interface of it or download it and use in Python. And if I give the picture to this model, it would tell us what animal that is. So in this case, it correctly says it's a wallaby. And that's the top matching image from that data set, the training data set they have used, right? Now, that's great. Then I go and take another picture of another animal. And again, I'm wondering what animal that is. I want to give it to the model and see the output of the model. Well, it's probably a bit difficult to ask this here. I wanted to ask if anyone would like to guess what would the output, what would be the output of the model. A hint is that is not going to get it correct. So, you know, all those cat and dog videos online. So it says it's a cat, which is obviously wrong. So we have two images of albino wallaby and one wallaby, and then it seems, even though they're the same view more or less, it got it wrong when it was a albino wallaby. So maybe that's the view. Let's take a photo of the same animal from another view from the side, and this time the model gets it right. Shows us the correct match. Now we go and take another photo. Here it's rather obvious to us what animal that is, but as we want to test our model, we give it to the model, and probably you're going to guess what. Is not going to get it right because albino gorillas are just rare in the nature. So probably it's very unlikely they have enough training images of that animal. And your guess would be correct. No matter how many images from what view you show of this gorilla to the model, it never gets it right. So with that example in mind, we see that how the model does a perfect classification for some animals, does an okay job sometimes for some animals, and always gets it wrong for some other animals. So that kind of gives us an intuitive definition of bias in computer vision and machine learning models. So what we can do about that? In the next few slides, I'm going to talk about that. From reading the literature and the recent research in this field, basically, there are three steps that have emerged. And that's first, understanding and the system that the training data is coming from. And that's the system also the model is going to most likely be integrated into. So we need to understand that system, and the way to understand is to model it. All the variables and attributes in that model. Then after that, we need to come up with a way to measure the bias in a model. And we all know that what gets measured gets managed. So that's a necessary step. And the third step, the final step is that, okay, now we have the tools. We need to go about and build our model with less bias or no bias at all. And all three turn out to be quite challenging. All there is under active research. So I'm going to just look at a few examples for each step, and hopefully that kind of encourages people who are interested in this field. And I'm hoping that more people will be interested in to take analyzing and studying bias in CV and ML models more seriously. So that's the question, that why would we care about even that as an engineer or as a researcher? To me personally, I think the best argument for that is that models that we develop could impact a large number of people because of how easy it is to deploy software at larger scale versus if, say, you're a biased person, as a single person, you are not going to impact that many people. And so hence the importance of this topic, that as engineers, we should take this more seriously. With that, I'm going to, as I said, I'm going to talk about a few examples of those 3 steps in the literature, but all of those links are in a repository we have created public on GitHub. We call it Awesome Bias Mitigation for algorithmic bias mitigation. We have papers, talks, code, and so on. List. We will be more than happy if you find some research paper or talk that you think is relevant. Please go ahead and either send it to us privately, or even better, to create a pull request. And we are trying to keep this, maintain this curated. So all the research engineers who are interested could find this hopefully a useful resource. All right, so let's talk about the first step. As we said, that's the system that most likely the training data is coming from, and our model is going to be integrated into. I found this talk by Hani Farid probably one of the best examples for this. Why do we need to start from there? So he talks about a model that in the courts in the US, they use to decide on bail. And even though this model as an input, it doesn't have the ethnicity, ethnicity or race as a variable, but it turns out to be a racist model. So he explains in this talk how he went about reverse engineering that model to find out that there is another variable that is strongly correlated with race. And that correlation exists in the training data, in the data that has been collected in the system, from the system. And so hence, this hidden bias has been introduced into the system, into the model, and it might not be obvious when you look at the input. You say, there's no way, there's no ethnicity or race in the model, so there's no way to do that. But if you model the system, you see where that gets introduced, the bias gets introduced into the model. And so one of the recent, a branch of work that is more recent is more in support of causal models. So this paper in Nature, I found it quite interesting. It's probably a good description of that approach, and why, what are the benefits of such approach, creating causal models. So you don't rely only on correlation, but by understanding the causal relationship between variables, you have a better model of the system and potential sources of bias. So here I have a kind of oversimplified example of that. I'm going to briefly explain. Say you're training a computer vision model, you already know image quality is strongly correlated with accuracy of the model. So in the sense that if you give it train your model with low quality images, the accuracy would not expect to do well. And if you give it high image quality, then you would expect your training images all are high quality. Then the accuracy of the model is going to be better. So say you have paid people to go take pictures of some objects, say their cars around the world, or their houses, or some other object. And after you train your model, you see there's a strange correlation in the data that some images, it does just poorly for it. So for some regions, images are taken in some certain region, and they're just, the model doesn't do well for them, and for some other regions, it does much better. So there's some kind of bias based on region. And then if you try to maybe, like as I said, this is like an oversimplified model, you see that, okay, I have asked people to take images using their cell phones, and it turns out that in some areas, they might have lower quality cell phones. The images are taken on hands are of lower quality, and then those are going negatively to impact the accuracy. So you see how that understanding the system can help find the source of the bias in the model. Then this is all, the next step is even more challenging, and that's coming up with a way to measure bias. So this example, these two equations, I briefly, in a moment I will explain what they do. These are taken from a competition, a challenge in the European Conference on Computer Vision, ECCV, a couple of weeks ago. And so in a sense, these two equations, what they do is that they measure the difference in accuracy between two groups of people based on some certain attribute. And they define bias as that, the difference between, the maximum difference between two groups of people. So you find two groups of people who have the largest amount of accuracy difference between them for a certain attribute. So that could be, that certain attribute could be the skin color, or a skin tone, or age, or gender. So of course you could ask, what is accuracy? Here in this particular case, they were using the area under curve. But you get the sense that, okay, this is vague. Why there are so many arbitrary decisions have been made to come up with such an equation? You might see some resemblance to generalization gap, but still you see that it's kind of a subjective metric. You could come up with many other ways, and that's there are lots of other papers that argue against even using this method. And the last step is now, okay, you can measure it, you can model the system. How would you build a model that is less biased? And so this is representative of a class of approaches that they use Bayesian methods, apply Bayesian methods to deep neural networks. So to understand this, just look at that arrow at the top left. So I'm just pointing, showing a point that is very far from the orange and yellow points. Those are the training points. And the intensity of the blue color shows the confidence of the model. So a deep network usually is very confident even at points that are very far from the training points. And that's a bad thing. That's one of the causes of bias, because you're wrongly overconfident about a point that you should not be. So in this model, this approach, after applying the Bayesian methods, like you look at the same point that's far away from any training point, and we see now correctly, it assigns a very low confidence point to that. So this is an internal work we have done several months ago. We worked on this. We came up with this approach. When we are, so which is probably is interesting for people to see this. So when we are working on algorithms to reduce bias and so on, one of the approaches we use is that training very simple models that the output or the embedding space is low dimensional, so we can visualize it. In this case, it's a two-dimensional space. And when we are applying different methods, we can understand what's happening during the training process, not after the fact that the training has stopped. So we can have a deeper understanding of the impact of those methods that we are trying on the training process. And to close the presentation, I think I should share 3 research questions, and that I believe they are quite important, and more people should work on this. And we are certainly working at Trueface on these problems. Will be different. And why I think these are important, because if they are solved, there are solutions for them, and everyone will benefit from them. So the first question is, how is that even possible to measure the bias or evaluate a model's bias without using any real data? So you just look at the model and judge its bias or generalization. And why that's important is that your test data itself, it could be biased, you know, and then so if you just don't rely on that, then you don't have that problem. And the second question that we are interested in is, can we get to that when the model gives us a confidence about a prediction, can that be a true prediction, not overconfidence about something that's completely wrong? So like the example I just showed, there's a lot of work that needs to be done. It's still there to perfect it. And the last probably and the most interesting is this. Can we have face recognition models as an example of other computer vision models that it's trained on images that are not face images, or at least human face images? So that's a very interesting thing. We're working on it. And if that's, you see, if that's that happens, if that's possible, then all the concerns about privacy and such, they are not there yet anymore. So like the bias and so on, because you're saying basically that bias is coming through our training data, and if your training data it doesn't even have human faces, and then you can control that much easier. All right, so with that, that's the end of the presentation. I don't know if we can answer, go to the QA. Let me see, actually.
Thanks, Mosalam. Feel free to type any questions in the